Okay class, this is lab 2-2. This is series circuits voltage relationships. What I've done is I've set up the loads according to what the drawing is in your next figure. The purpose of this lab would be to demonstrate that the sum of all of the voltage drops has to equal the source voltage being output. Okay? So I've got a 60 watt bulb here for load 1, a 100 watt light bulb for load 2, a 150 watt light bulb for number 3, a 200 watt light bulb for number 4, and then our cone heater over here at our 660 watts for load number 5. That's coming back to positive. So current is flowing out of the negative all the way through these jumpers and loads back to the positive and back home. I've got a voltmeter here connected up to the source to verify what voltage is being output to the loads. Okay, and then I've also got a separate multimeter here that I've put on DC volts as well. And what that will do is that'll tell me the voltages that they're going to ask us to do. In the steps in the lab, what they're going to ask us to do would be to verify the voltage at the source, and then based on the voltage that we increase it up to, take your readings across each of the loads, and then what they'll ask us to do would be to either remove loads or short loads out, things like that. It should be pretty straightforward, so let's give it a go. Now, we power it up, we turn our power supply up to 120. Okay, and it's almost a little misleading to see if this is actually working properly, because you anticipate, I'm just trying to get her to 120 here, we're at 120 even right there. I'd even highlight that if I can. I don't know if the camera can pick that up. So it's 120.1 now, so pretty close. In a series circuit, if no current was flowing, none of these loads would be lit up, okay? Or if we had an open, such as if I were to unscrew one of these light bulbs, you can see that what I've done is I've created an open, therefore it's preventing any of the current flowing through those light bulbs. Very similar to Christmas lights, old Christmas light string. When one light bulb burnt out, then the rest of them would burn out as well, okay? So it's a little misleading that this circuit is working properly, because these light bulbs here, you would anticipate them coming on and being bright. However, what you will find though is that this 60 watt light bulb, because it's the brightest, it has the greatest voltage drop across it, and then there's leaving next to nothing left for all of these loads over here. Okay, so let's just give this a shot. So it says we power everything up in step 1, 2, and 3 after we connected it all up. Step 5 says, using the appropriate DC voltage range on the multimeter, carefully measure the voltage drops across each of the loads and record them in table 1. So, table 1 says, what is the voltage across load number 1? Load number 1 is that 60 volt light bulb. Okay, so I'm just going to set this up maybe over here so we can see it. Okay, alright, I'm on volts DC. I'm putting my test leads in there and there, and I am metering 75, very near 76 volts. We're going to call it 76 volts at load number 1. Load number 2, we're going to see a significantly less amount there. Okay, but because that element is still heating up, it's going to be higher than the other ones. That is sitting at 23 volts. Actually, I'm going to round it up to 24 just to make our math easy. Okay, so call that 24 volts. So we've got 76 at load 1 and 24 at load 2. We're already at 100 volts, and we have 3 more loads to deal with over here. Okay, load number 3, that would be the next step they want us to meter. That's 10 volts there. Okay, so if we have 76, 24, and 10, we're at 110. And we've only got a 120 volt source, so that means that the 200 watt bulb and the high resistance heater there is going to have the smallest amount of resistance across, or the smallest voltage drop across it. Okay, so load number 4, the 200 watt, is sitting at 4, call it 4 volts. Okay, meaning that at load 5 we should see 6 volts left over, or very near that. Okay, So this is saying 7.11. I was doing some rounding along the way. In order for things to work out proper, you can record that as 6 volts. Okay? So, that's that. So now we're at the end of step 6. They ask us to turn our power off. And then the next thing they want us to do is to short circuit in step number 7. Short circuit number 4 by placing a connecting jumper across its 2 terminals. Okay? So we're going to create a short circuit across load number 4 by putting a jumper there. So in doing that, we've reduced that high amount of resistance in the circuit. Okay, we've taken that out of the equation because current takes the path of least resistance, so it's bypassing through here. So by doing that, we should have more voltage available at the other lights and than the cone heater. So you're probably going to see these light bulbs changing in the way that they were from previous, and maybe potentially that cone heater starts to get a little bit warmer. So let's power up and see what happens. So what has happened here? We've got that one still burning brightly, this one's still trying to do its job. These guys here, I don't see much of a change there or much of a change there, but we won't know until we prove it. So in our first load 1, the new voltage drop across here is now basically 79 volts. Okay, so if we got 79 there, we've gone up 3 volts across that by short circuiting that one load. Load 2, we've got 12 volts. Oh, sorry, wrong gauge. 24 volts. Okay, so we're now sitting roughly at 103. That means the remainder of this and that cone heater must see the combined amount of 17 volts. So load number 3 is sitting at 10. Okay. If I go across load 4, this point, or that terminal there and that terminal there, are the same potential. So we should see very near 0 volts across there, which we do. So load 4 is 0. And then load number 5, which is the cone heater, should see the remainder of the voltage required. So that's sitting at 8 volts. Okay, 7 volts. Okay, and that should work out, because we needed 17 volts on top of the 103 that we already had, and that's what we get. Okay, so that lab worked out pretty well there. Next step, what do they ask us to do? Adjust to 0, turn the power off, remove the short circuiting jumper across load 4. Okay, and then remove the jumper from between loads 3 and 4. So this guy there, we're removing it. And now we're creating an open circuit. So in an open circuit, no current is flowing through these loads because it has no complete path. So we should see 0 volts there, 0 volts across that load, 0 volts across there, 0 there, and 0 there. However, across the open, we should see the source voltage. So I'm going to power up now. No lights are on, so we know that there's no current flowing in that circuit. And we can very quickly meter and see that we got 0 across load 1, 0 across load 2, 0 across load 3, 0 across load 4, and 0 across load 5. However, across the open, we see that we have the 120 volts. Okay, so you can record that. Load 1 was 0. Load 2 was 0, load 3 was 0, load 4 was 0, load 5 was 0, and the open saw the 120 volts. Because that is in effect an open switch. If I were to turn that off, replace that jumper, okay, we have effectively turned that circuit back to what it was to start with, and everything is going to be lit up the way it was intended. Okay? So high resistance values have a greater voltage drop across them. A lower resistance value has a smaller amount of voltage drop across it. That's why the 200 watt and that 660 didn't see a lot, but that 60 watt light bulb has the greatest amount of resistance in this circuit, so it's seeing the greatest voltage drop across it. Okay, power down, clean up my work area, and we can go over the observations and conclusions as a class later on. Thank you for that. That was Lab 2-2, Series Circuits, Voltage Relationships.